Hello students, continuing in the chapter of alternating currents, in the third and last lecture, let us discuss the concepts of average power consumption in AC. We should also discuss what is the meaning of LC oscillations and some of the aspects of our leftover topic, that is parallel RLC circuit. The first discussion today we are making, that is of what is the average power consumption in an alternating current circuit. For this particular discussion, let us consider a general RLC circuit in which, let us suppose, the EMF imposed, which is alternating, is E naught sin omega t, and let us suppose the elements are resistor, inductor and capacitor. You have already seen by way of the impedance triangle that the resistance can be plotted on horizontal axis like this. The total reactance, we had said that, let us suppose it is the resultant of reactance of inductor and capacitor. For the time being, let us suppose I am assuming that the inductor right now is dominant compared to capacitor. It is inductive dominant circuit. That is why the net reactance I am showing on the upper side. And if I take the Pythagoras of these two, that is the resultant, it will be giving you the phase angle phi and the total impedance of the circuit Z, where you know that the Z will be Pythagoras of R and the total reactance of the circuit, that is R square plus omega L minus 1 by omega C whole square under root. This is the net impedance of the circuit available, and the phase angle you see, that is phi. Now this phase angle phi will be playing its role so long as EMF is concerned. Here you can say that EMF is E naught sin omega t, but since the total impedance is involving a phase angle that is shown here, so the current will be lagging by an angle phi. And you can say I is equal to I naught sin omega t minus phi. This is a general expression of, you can say, current we have written down when the reference E is equal to E naught sin omega t has been given to you. If you want to show it on a phasor diagram, you can always write it as EMF like this and current is lagging by an angle phi. Since it is lagging, so I am writing it as minus phi. Now if you look at the relation between E naught and I naught, then you should know that I naught can be written as E naught by Z. What is E naught? E naught is the peak value of EMF which has been imposed on the series RLC circuit, and based on which you have the peak current I naught related to EMF and total impedance like this. If you are interested in finding out the RMS current, then you have to use the RMS value here divided by the total impedance of the circuit, and that will be IRMS. So you can see that in this kind of circuit the general value of current has been written this way. आप कह सकते हैं कि ये इंस्टेंटेनियस करंट की वैल्यू हो गई और ये इंस्टेंटेनियस ईएमएफ की वैल्यू हो गई. नाउ यू हैव द एम in this particular exercise to find out what is the average power consumption. Let us suppose you are denoting average power consumption as P average. You understand? So you can invoke the concept of the instantaneous power which we have discussed already in direct current circuit. अगर हमें एवरेज पावर की बात की जाए तो उसके लिए पहले हम इंस्टेंटेनियस पावर देखते हैं. अगर आप देखें कि अगर मुझे एवरेज पावर कैलकुलेट करना है, दैट मीन्स आई शुड नो व्हाट इज द इंस्टेंटेनियस पावर. इंस्टेंटेनियस पावर विल बी रिटन एज E इंटू आई, EMF इंटू करंट. अगर आप यहां पे EMF और करंट की सिचुएशन देखें तो लेट अस सपोज EMF is denoted like this, then here the current is lagging the EMF by an angle phi. अगर ये zero angle है, ये phi angle है, so this is the instantaneous of value of current you have shown, and that is the instantaneous value of EMF you have shown. Now consider a very small time interval dt. Then you can see in a very small time interval dt, which I have indicated here, the current value is I and this instantaneous current has been denoted here. You see that? अगर आपने सर्किट में EMF इंपोज किया है और जिसकी वजह से करंट फाई एंगल से अगर लैग कर रही है तो उनकी इंस्टेंटेनियस सिचुएशन इस तरीके से दिखाई जाएगी, जिसमें आप देख सकते हैं EMF अगर ऐसे जा रहा है तो करंट फाई एंगल शिफ्ट होके मूव कर रहा है. तो लेट अस सपोज किसी भी एक पर्टिकुलर टाइम पे आप करंट की और EMF की दोनों की इंस्टेंटेनियस वैल्यू अगर देखें तो EMF की वैल्यू ये है जो कि आपने यहां पे लिखनी है और करंट की वैल्यू ये है जो आपने यहां पे लिखनी है. दिस इज द इंस्टेंटेनियस पावर राइट नाउ आई एम सेइंग, एंड E और I की जो इंस्टेंटेनियस वैल्यू है विच यू हैव ऑलरेडी रिटन हियर. एंड अगर इस इंस्टेंटेनियस पावर को आप इतने स्मॉल टाइम इंटरवल dt से मल्टीप्लाई कर दें तो दिस इज द स्मॉल अमाउंट ऑफ हीट विच इज जनरेटेड इन द सर्किट ड्यूरिंग दिस टाइम इंटरवल dt. और अगर आप इस पूरे हीट को पूरे साइकिल टाइम कैपिटल T में इंटीग्रेट करें तो ये हमारा टोटल हीट जनरेटेड इन द सर्किट आ जाएगा. यू अंडरस्टैंड? एवरेज पावर को आपने स्मॉल टाइम इंटरवल dt से मल्टीप्लाई किया है तो दिस इज द स्मॉल अमाउंट ऑफ हीट जनरेटेड विद इन दैट टाइम इंटरवल dt. इसको आप पूरे टाइम इंटरवल के लिए इंटीग्रेट कर रहे हैं, सो आपको एक पूरे टाइम इंटरवल का हीट जनरेटेड मिल जाएगा. नाउ अगर आपको एवरेज पावर कैलकुलेट करना है तो दिस इंटायर हीट जनरेटेड शुड बी डिवाइडेड बाय द टोटल टाइम पीरियड ऑफ द साइकिल एंड दैट विल मेक द डेफिनेशन ऑफ एवरेज पावर. यू अंडरस्टैंड? एवरेज पावर की पूरी डेफिनेशन ये होगी एंड एसेंशियली यू हैव टू कैलकुलेट द वैल्यू ऑफ दिस, यू हैव टू डिराइव द वैल्यू ऑफ दिस टू गेट द एवरेज पावर इन्वॉल्व इन द सर्किट. नाउ इफ यू सब्स्टिट्यूट द वैल्यू ऑफ EMF एंड करंट, अगर आप इंस्टेंटेनियस EMF और इंस्टेंटेनियस करंट की वैल्यू इस एक्सप्रेशन में सब्स्टिट्यूट करेंगे, देन एवरेज पावर का एक्सप्रेशन हमारे लिए इट विल बी समथिंग लाइक E0 sin omega t. I have substituted for this EMF you see, and for current I have to substitute I0 sin omega t minus phi. You understand? Now this particular thing is to be integrated between 0 and capital T because you are integrating with respect to time. This is the total heat generated, and once this will be divided by the total time period capital T, then that will make the average power consumption in the circuit. You understand? So it is involving the concepts of integration. So let us put some exercise over that and try to find out what is the average power consumption. If you look at the entire terms here, there are some of the things which are constant, that is E0, I0, capital T, all these things are constants, and your final exercise is something to integrate sin omega t and sin omega t minus phi. So let us suppose I am interested in finding out the integration of sin omega t multiplied by sin omega t minus phi with respect to time t between 0 to capital T. बिकॉज बाकी सारी चीजें इसकी कांस्टेंट है, दैट इज ई नॉट, आई नॉट, टी, ये सारी चीजें इसकी कांस्टेंट है, उसको आपने बाहर निकाल लिया है, एंड दिस इज बिकमिंग योर इंटायर पावर एवरेज. सो अभी हमारी कॉन्सेंट्रेशन सिर्फ इतनी चीजों पे है, बिकॉज ई नॉट आई नॉट डिवाइडेड बाई टाइम टी, वो सारी क्वांटिटी एक कांस्टेंट क्वांटिटी है. इन केस यू एक्सपैंड दिस थिंग, देन यू सी it will be sin omega t here for this, and this sin omega t minus phi can be written as sin omega t into cos phi minus cos omega t into sin phi. This is the expression I have got by using the concepts of trigonometry. Then you have dt here and the integration sign. And of course, all these E naught, I naught upon capital T is involved. You understand? I have written E naught, I naught by T, and this is to be integrated between 0 to capital T. Now, you see that here you have two parts of the integration. अगर आप इतने पार्ट को देखें, तो you are expected to integrate sin square omega t इंटू कॉस फाई. अंडरस्टैंड? मैंने देखिए अभी यहां सिर्फ फर्स्ट टर्म को लिया है, साइन स्क्वायर ओमेगा टी, बिकॉज दीज टू आर टू बी मल्टीप्लाइड एंड टू बी इंटीग्रेटेड बिटवीन 0 टू कैपिटल टी. ये एक वन पार्ट हो गया. एंड एक दूसरा पार्ट इस इंटीग्रेशन का है, विच इज इन्वॉल्विंग साइन ओमेगा टी, कॉस ओमेगा टी एंड साइन फाई. सेकेंड पार्ट ऑफ द इंटीग्रेशन विच यू सी, that is involving sin omega t, cos omega t, sin phi. You understand? This is the second part of integration you are having out of the multiplication of this and this, and again this you have to integrate between 0 to capital T. Understand? हमारी इस पूरी डेरिवेशन का मेन एस्पेक्ट ये है कि यू हैव टू कैरी आउट दिस इंटीग्रेशन एंड फाइनली यू विल बी मल्टीप्लाइंग इट बाय ई नॉट आई नॉट बाय टी. नाउ डील विद देम सेपरेटली. अगर आप इसको इंटीग्रेशन 1 बोल रहे हैं, लेट अस सपोज दिस इज I1 एंड लेट अस सपोज दिस इज इंटीग्रल पार्ट 2. ये सेकेंड पार्ट ऑफ हमारा इंटीग्रेशन है. हैंडल देम वन बाय वन. अगर आप साइन स्क्वायर ओमेगा टी कॉस फाई को इंटीग्रेट करते हैं, यू कैन सी इट हियर, साइन स्क्वायर ओमेगा टी कॉस फाई, इफ इट इज इंटीग्रेटेड बिटवीन 0 टू कैपिटल टी, देन यू सी कॉस फाई इज अ कांस्टेंट क्वांटिटी. क्योंकि फाई जो है वो एक फेज एंगल है, इट्स अ कांस्टेंट क्वांटिटी, दैट कैन ऑल्सो बी टेकन आउट ऑफ दैट इंटीग्रेशन साइन. एंड sin square omega t can be written as 1 minus cos 2 omega t upon 2 to be integrated between 0 to capital T, because the variable is time t. कभी भी sin थीटा या cos थीटा या cos 2 थीटा या sin 2 थीटा, इन सब को इंटीग्रेट अगर आप एक पूरी साइकिल के लिए करते हैं, so that comes out to be 0. Always remember that. For example, here you see 1 by 2 will be working as a constant, but this cos 2 omega t, once you will be integrating between the total cycle, then automatically that value will be coming out to be 0. Therefore, if you carry out this integration, you will simply be getting this cos phi as a constant, and here 1 by 2 integrated with respect to time, that will come out to be capital T by 2. You understand? So this is the first part of your integration, जिसको आपने I1 से indicate किया है. तो I1 is coming out to be having a value like this, cos phi into capital T by 2. This is the first part of the integration you have done. यहां पे हम लिखना चाह रहे हैं कि I1 की वैल्यू फाइनली जो है, that is T by 2 into cos phi you are obtaining. This is the integration of the first part of the entire integration. Now once you are getting down to the second part, अगर आप इस पे concentrate करें, Then here you can see this is sin omega t into cos omega t. This sin phi is a constant, so that can be taken out of that integration sign. In case you carry out this integration, then you see this sin phi I am taking out of this integration sign because this is a constant quantity. And sin omega t cos omega t can be written as sin 2 omega t divided by 2. And then you have to carry out this integration in between 0 to capital T. Understand? This is the second part of the integration, in which again you can see you are involving a term which is sin 2 theta kind of concept. So as I said, if you are integrating sin theta or cos theta, or say sin 2 theta or cos 2 theta over the complete cycle, then that comes out to be 0. So my second part of the integration boils down to a value 0. You understand? If you now consider the complete integration, then the first part is giving you some value cos phi into t by 2, but the second part is giving you an integration that is coming out to be equal to 0. Therefore, if you transfer this entire expression here for P average, then I must say that P average value came out to be E naught I naught upon T. This was the beginning part of the integration. You understand? And the total thing which you are seeing, that is simply cos phi into T by 2. So here I can substitute that is cos phi into T by 2. This is the total expression of average power I have got. If you look at this expression carefully, this becomes P average as E naught I naught cos phi upon 2. You understand? This is the kind of derivation we had so long as the average power consumption in an alternating current circuit is concerned. Now you will have to have several discussion on this average power of consumption in alternating current circuit has come, how it can be manipulated for our convenience. Here the factor 2 which you are getting, that can be divided as root 2 multiplied by root 2, and it can be allocated to these E naught and I naught. So let us have several discussions which you are obtaining on the expression of average power. Let us have a discussion on average power consumption. Just now you have derived the expression P average as E naught I naught upon 2 cos phi. Remember that this 2 can be divided as root 2 multiplied by root 2. It can be written as E naught by root 2 I naught by root 2 cos phi. And if you remember that E naught by root 2 was also equal to the RMS value of EMF. What is this E naught? E naught is essentially the peak value of EMF, and I naught is the peak value of current. So if you are dividing it by root 2 and root 2, so that makes it ERMS into IRMS into cos phi. You understand? So this is the modified expression of average power you have got. This is the kind of expression you can say all the time you are using. Again, you should recapitulate that the cos phi term which you have, that is coming out from our impedance triangle. This was R, this was equal to X, and this was equal to Z. And this angle phi which you see, that is shown like this in the impedance triangle. Just now you had shown it. Now you see that this cos phi is called power factor, and that can be written as R upon Z. Here we are saying that cos phi, the term cos phi you are having here, this is called power factor. This is called power factor, and this is equal to, you can see this is R by Z. From the impedance triangle, I am getting the expression of cos phi as R by Z. Here, the term you have got ERMS into IRMS. This is called apparent power. This is called apparent power, because when you happen to discuss the thermal or heating effects of current, then there we happen to say that EMF multiplied by current happens to be the power. यहाँ पे भी ERMS and IRMS उनकी प्रोडक्ट को हमने पावर तो कहा है, लेकिन दिस इज apparent power because it appears that this is the power. But remember that in the expression of average power, it is not only ERMS, IRMS, rather a term of cos phi is also involved. You understand? पावर एवरेज के एक्सप्रेशन में सिर्फ ERMS और IRMS का रोल नहीं है, यहां पे एक और भी टर्म जिसको आप cos phi कहते हैं उसका भी रोल है. दैट इज वाई दिस इज बीइंग कॉल्ड पावर फैक्टर, एंड this much term is called apparent power. So you should understand that average power is apparent power multiplied by the power factor. Now if you consider all the elements one by one, then you see for resistors, for resistor only, मान लीजिए सर्किट में सिर्फ रेजिस्टर है, that means reactance is absent. अगर यहां पे reactance absent होगा, that means the value of x will be 0. और x अगर 0 हो जाएगा तो z और r दोनों सेम हो जाएंगे. यू अंडरस्टैंड? अगर प्योर रजिस्टर देखा जाए तो यहां पे x की वैल्यू 0 हो जाएगी एंड r एंड z दोनों सेम हो जाएंगे. देयरफॉर cos phi की वैल्यू 1 के इक्वल होगी, बिकॉज फॉर प्योर रजिस्टर z एंड r दे आर सेम. और आपने जब पावर फैक्टर की वैल्यू r बाय z लिखी है तो दिस इज cos phi इज इक्वल टू 1, एंड इन दैट केस P average is simply ERMS into IRMS होगा. और अगर IRMS के बारे में आप देखें तो ये ERMS अपॉन रेजिस्टेंस के इक्वल हो सकता है. सो इट कैन ऑल्सो बी रिटन एज ERMS होल स्क्वायर अपॉन द वैल्यू ऑफ रेजिस्टेंस. Understand? The complete thing will be coming out like this. Or maybe if you feel like writing in terms of IRMS and R, then you know that ERMS can be written as IRMS into R. Understand? So this can also be written as IRMS whole square into resistance. Now you can see for pure resistors, the average power consumption is having the same kind of expression as you have for direct current circuits. There you had V square by R or I square R. These are the expressions you had for direct current. और वही expression यहाँ पे alternating currents के लिए भी आएगा अगर सर्किट में हमारे पास प्योर रजिस्टर कनेक्टेड है. बट इफ यू थिंक फॉर प्योर इंडक्टर, अगर एक प्योर इंडक्टर देखा जाए, देन यू सी फॉर प्योर इंडक्टर R इज इक्वल टू 0. प्योर इंडक्टर के लिए R इज इक्वल टू 0 है क्योंकि वहां पे सिर्फ रिएक्टेंस होगा. देयरफॉर यू कैन सी द पावर फैक्टर विल बिकम 0. फॉर प्योर इंडक्टर R इज 0. देयरफॉर यू कैन से द पावर फैक्टर cos phi that is also equal to 0, and in that case the average power consumption that comes out to be 0. This is a very important thing to learn, that in a pure inductor the power average consumption is equal to 0. Maybe the inductor has the tendency to change the current value. अगर इंडक्टर आप सर्किट में लगाते हैं तो हमारे करंट को वो कम कर देगा बिकॉज इट इज इन्वॉल्विंग रिएक्टेंस, बट द एवरेज पावर कंजम्पशन ओवर दिस दैट इज 0. दैट मीन्स ये आपसे कोई भी पावर कंज्यूम नहीं करता है. बट करंट को रिड्यूस कर देता है. रिड्यूस करना, दैट इज ऑल्सो कॉल्ड चोकिंग, एंड दैट इज वाई दिस प्योर इंडक्टर इज ऑल्सो कॉल्ड choke coil. You understand? In our day-to-day discussion, you will be finding that a mentioning of choke coil has been done. Essentially, this choke coil is nothing but a pure inductor. The function of this choke coil is wherever in the circuit you want to just reduce the current without any power loss, then pure inductor is involved. Similar kind of function can be done by pure capacitor as well. But remember that, for example, in our household tube light, you see we need to reduce the current. जो भी वोल्टेज सप्लाई होती है उसे हम रिड्यूस तो करना चाहते हैं, बट वी डू नॉट वांट टू यूज एनी लॉसेज ऑफ पावर. देयरफॉर आप देखेंगे उसके साथ एक चोक कॉइल भी हम कनेक्ट करते हैं. द ट्यूब इज वर्किंग एज रेजिस्टर, along with that we happen to add a choke coil so that the current is reduced without any power loss. This is the function of choke coil, which is essentially based on this fact that its power factor is 0 and the average power consumption over the circuit is 0. Now if you consider pure capacitor, let us suppose in the circuit you are talking about pure capacitor. For a pure capacitor, again you can say like inductor, the resistance of the circuit is 0. So for pure capacitor R is equal to 0. Once again you can say power factor is 0. Therefore average power consumption, that is equal to 0. And you can say, for that matter, inductor and capacitor, they are called wattless elements. Wattless elements because the average power consumption over such devices, that is 0. So you can say pure inductor and pure capacitors are called wattless elements. They are called wattless elements because they are not consuming any power over the complete cycle. You understand? And the way you have defined this wattless elements, in the same fashion you can define wattless current as well. What is the meaning of wattless current? You see, here in the chapter of alternating currents, we are treating everything as a vector quantity. EMF is being treated as vector, current is being treated as vector. If you are talking about wattless current, then you see in the expression of power average, you are having ERMS into IRMS into cos phi. So this is the cos phi term, or you can say if you have say current IRMS which is making an angle say phi with the reference EMF, then it is the cos component of this effective current which is involved in having power consumption, but the sine component of this average current is not consuming any power. It's only the cos phi which is involved in power consumption. The sine component is not involved in power consumption. That is why the sine component of RMS current is called wattless current. You understand? So wattless current means what? The sine phi component of this RMS current is called wattless current. You understand? Now it is not always necessary that we have the situation in which only pure resistor or pure inductor is involved. In case all of them are involved, then let us again make certain manipulations so long as this average power is concerned. In general, you have seen that the average power is equal to ERMS into IRMS into cos phi. Now the essential thing to learn here is that ERMS is also equal to IRMS into Z. अब हमारी सर्किट में मान लीजिए एक जनरल सिचुएशन है जिसमें R, LC सारे ही इन्वॉल्व हो सकते हैं, तो ERMS will be written as IRMS into Z and this cos phi was written as R upon Z. In case, let us suppose you make this substitution into this exercise, then you see P average can be written as IRMS into Z. This substitution you have made for ERMS. Then the next term you have, that is IRMS. I have written down IRMS. And this cos phi I am writing as R upon Z. And here you can see this Z will be cancelling, this Z will be cancelling this Z in the denominator, and finally you will be having an expression like power average is equal to RMS current square into R. You understand? जैसे हमने डायरेक्ट करंट सर्किट के लिए देखा है, so power average can be written as IRMS square into R. But do not draw any over conclusion out of this expression in the sense that अगर आप यहां पे ERMS square upon R लिख देंगे तो हमारी सिचुएशन रॉन्ग हो जाएगी. You can check that. Now you can see what I am trying to say, that try to replace this IRMS by ERMS and Z. Then you will be getting ERMS multiplied by ERMS upon Z. This is the replacement I have made for RMS value of current, and for cos phi you substitute R by Z. Then you can see it is not coming out to be ERMS square upon R, rather you are getting a term like ERMS square into R upon Z square. You understand? एक जनरल सर्किट के लिए ये एक्सप्रेशन ट्रू है. दिस एक्सप्रेशन इज ट्रू फॉर प्योर रेजिस्टर एज वेल, बट फॉर जनरल सर्किट यू कैनॉट यूज ERMS स्क्वायर अपॉन R. Only when you have a pure resistor circuit, then only Z is equal to R, and then you can substitute expression E square by R. This is the kind of, you can say, warning I am giving to you, that just by looking at this expression, do not jump onto the expression ERMS square by R. Rather, you have the correct expression as this, so long as the average power consumption is concerned. You understand? So these are some of the things you have to bear in mind. If you remember, in the last lecture we had talked about resonance. Then you see at the time of resonance you have Z is equal to R. So at resonance you can say since Z is equal to R, therefore you can use any of the expression. P average is equal to IRMS square into R, or it can be written as ERMS square upon R. Any of the terms you can use for average power consumption at the time of resonance, because this is the kind of expression which is saying that the circuit is involving as if only pure resistor. So that is the discussion we had on average power consumption. Now let us discuss a topic called LC oscillations.